good understanding of what are vector spaces. Okay, fine. So before going to the definition, we will start with some examples to have a motivation of what are vector spaces. All right. Okay. So what do we already know that we will use to understand the vector spaces? We know about what are system of linear equations. So let's start with the system of linear equation. Ax is equal to b, where A is an m by n matrix. Okay. So we have seen a few ways of identifying solutions. One of the technique which I mentioned just now is the Gauss elimination method, right? So any other method, can anyone remember and tell me here? What other techniques can be used to solve a system of linear equation?
Kramer rules and
Kramer's
inverse.
rule inverse of
Kramer's rule is not
So
applicable when m is not equal to n.
yes, so for Kramer's rule and inverse solutions and all, you need the matrix first of all to be square and also invertible. Both these conditions are required for the other two techniques, but Gauss elimination is more general, right? Okay, good. So now consider this particular set S, which is set of all x in Rn such that Ax is equal to 0. So Ax is equal to B, we call it non-homogeneous, and Ax equal to 0, we call homogeneous system, right? So now what is this S, this set S exactly? This is nothing but set of all solutions of the system Ax is equal to 0, right? So this is all the solutions of the system Ax equal to 0. What do you already know about this set S? Is this always non-empty? What is the information you know about it?
It may have
Is it non-empty?
trivial solution or, no, or non-trivial infinite solution.
Yeah, so always it will have a trivial solution. So 0 is always in this set because a times of 0 is 0. So it means 0 belongs to S. So this is always non-empty, right? And it contains the, in the case, it is the 0 vector. Okay, so S is either a singleton set, so which is the trivial case we see. This is the trivial case. And what was the other case which you were saying? Or it contains?
Infinite.
Yes, infinitely many elements.
Ma'am, S is either. Can you please repeat
Yeah.
the
So
second line?
yeah, so S, you see that either it is a singleton set. Singleton set is in the sense that S is either just singleton 0 or S is infinitely many elements. S contains infinitely many elements, right? So these are the only possible solutions for the set S. Okay, fine. Okay. So,
Uh,
for example, yeah.
would you mind explaining vector space once again because I got disconnected?
0 because it is a homogeneous function. No?
Yeah, because of the right hand side is 0, 0 belongs to S. I have not yet started what are vector spaces. No, we have not yet
Okay.
used the term. Okay, we are just in the motivation part. So where we are just trying to understand the set S here. Okay, fine. Now, what are the things we can see more about the set S? Let us assume the case when S is an infinite set, because this case is not really interesting to understand these properties. So I'm going to consider the case where it is infinite. Okay, so what we can observe, suppose you have two different elements in S, then what can you say about the sum of these entries? It need not be different, it can be same also. So you take any two elements in S, what can you say about the sum? Will it also be in S? So if V1, V2 belongs to S, from this what can you say? What can you say about AV1 and AV2? If V1 and V2 belongs to S, this is the definition. So if V1 belongs to S, so V1 is in Rn such that AV1
x
should
is
be
equal
what?
to 0.
So AV1 is 0 and AV2 is also 0, right? Because V1 and V2 are in S. So if AV1 and AV2 are 0, what happens to AV1 plus V2. So this now we can split it as AV1 plus AV2, right? And now these two terms are 0. So this becomes 0. So this means that V1 plus V2 belongs to S. Okay. So if V1, V2 belongs to S, then V1 plus V2 also belongs to S. This property is called additive closure. This property is what? Additive closure, or we can say the set S is closed under addition. The property is additive closure and the set S is closed under addition. It means what? You take any two elements in that set, and if the sum of those two elements is also in the set, then we say that the set S is closed under addition. Okay, fine. Now let's take
Can you give me example?
this is itself an example. So this is a set S here where this property is satisfied. Right?
As in real number.
Okay, in real numbers, suppose you take real numbers itself, what happens? The entire real number. If you add any two real number, will it be again a real number?
Yeah.
Okay. Now let us say the set up for rational numbers. You can again see that they are again closed under addition, right? Now there are several examples. We are going to see more and more examples following this. Okay. So now let's look at the next scenario. If alpha is in a scalar in the sense that it is a real number, and V1 is some element in S, then what can we say about alpha times of V1? Okay. So if V1 is in S, what do we already know? If V1 is in S, then we know that AV1 is equal, right? Now, what can we say about A times of alpha V1? Now, A times of alpha V1 can be written as AV1. Okay. And what do we already know about AV1? AV1 is 0. So, alpha times of 0 is 0. So, this means that alpha V1 also is in the set S. So, S is closed under scalar multiplication. Okay. So, this is scalar multiplicative closure property. Okay. So, you see that this set is satisfying these two conditions. Okay. Now, check closure under addition and scalar multiplication for some following sets. So, now consider this set which is a subset of, right? So, this is subset of R2. Now, can you check whether it is closed under addition? So, for closed under addition, what is that we need to do? What is that we need to do? We need to take two vectors, V1 and V2 from S, and we want to check whether V1 plus V2 belongs to S. Now, V1 and V2 belongs to S means it should be of the form, V1 should be of the form some x1 comma 0, and V2 should be some x2 comma 0, right? Now, what about V1, V2? V1 plus V2 is simply x1 plus x2 comma 0. Is it there in the set S or not? Yeah, it belongs to S, right? So this is closed under vector addition. Yes. Okay. Is this closed under scalar multiplication? For that, what we need to do? We should pick a scalar, right? And a vector in S. Now we want to see what happens to alpha times of V1. So V1 is already x1 comma 0. What happens to alpha times of x1 comma 0? Which is, okay, what happens to alpha times of x1 comma 0? So it is alpha times of V1. Okay, and this is alpha x1 comma 0. So again, alpha x1 is a real number. So this is again an S. So this is also closed under scalar multiplication.
Now, what is alpha?
Alpha is just a real number. Okay, any real number. Okay, fine. Now, can you try?
And from where?
Yeah.
Yeah. So from where we are getting V1 and V2? Is it from S?
From where we are getting what? What is your question?
I think
V1 and V2, vector V1 and
Yeah,
V2.
V1 I have clearly written that it is in S.
Uh, my question is from where we are getting.
See, what is the property of closed? See, we are asked to check closure under vector addition and scalar multiplication. So for closure under vector addition and scalar multiplication, this is what we have to do. We have to take any two vectors in S and check whether the sum is also in S, and we have to take any vector and see whether the scalar multiple is also in S. That is the question here, right? What's your doubt?
Okay.
Okay, fine. So let's try the
Yeah,
same
it's
thing.
clear now. Thanks.
Okay, fine. So let's try similar thing for this set. Yes, we want to check whether it is closed under vector addition first. So we have to take two vectors v1 and v2 in S. Okay. So how do they look like? Can anyone say how can we write v1? You take hint from the previous question and try. See, if the class is not interactive, not for
X1,
you. Yeah.
Y1, comma 1.
1 y1 comma 1
1.
1 y1.
Yeah. And what about v2?
x2 y2
x2 y2 1.
X2
1
Good. So now what about v1 plus v2? It is x1.
x1 is plus x2
Plus.
comma y1 plus y2 comma 2.
Is this there in the set? Yes.
No.
No. Right? This does not belong to S because this entry is not equal to 1. Right? Because in S, for all the vectors in S, the last entry should be 1. But here it is not equal to 1. So this cannot be in S. So is this closed under vector addition?
No.
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 Okay, what
Ma'am,
about,
what's
yes?
the what does the one indicate? I'm so sorry to butt in, but what does that one indicate after x and the y?
It's just the number. See, it's the set of all x. For example, if you just considering x comma 1, x in R. So maybe if you want to understand what does this set represent, maybe I will show you it in R2. So you can imagine something similar in R3 because R3 drawing is difficult. So I will show it in R2. So in R2, okay, in R2, now your y value is 1. So this represents all the points on this line. So if you call this as S, then this is your X, where this is Y equal to 1. This is
Okay.
Y equal to. Okay, so something similar, you can imagine a plane where all the Z coordinates are 1. Okay, this is in
Okay,
R3.
okay. All right.
Okay, fine. Okay, so now let's look at the closed under scalar multiplication property. So for that, let's take an alpha in R and we are going to look at V1 in S. What happens to alpha times of V1? So alpha times of X1, Y1, comma 1, which becomes alpha X1, alpha Y1, and alpha. So if alpha is not equal to 1, then can we say that this alpha is equal if will this be in bracket S? So this alpha need not be 1, right?
Yeah.
Not be 1. So in that case, this also need not be in S. So we can say that this is not closed under scalar multiplication as well. Is that fine? Yes?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Okay. What about this?
Yes, ma'am.
What about this set?
Can you please explain that again? Why alpha need not to be 1?
This set is not a vector.
So the last entry should be 1 for all the elements in S. For this entry as well as this entry, the last entry is not 1, so they are not in S. Got it? Okay. Fine. So now we are having this set S. So to just simplify, we are going to rewrite this set. How can I rewrite y in terms of x from this equation? Can anyone tell?
1 minus x.
Yes.
Minus x.
So I'm going to replace y with 1 minus x. So this will help us to do the calculations easier. Okay. So x comma 1 minus x. Okay. Now any two elements from S we are going to pick. Okay. Can anyone tell how V1 and V2 should look like? Make more space.
0, 1, 4, 1. Basically squares.
x1 comma 1 minus x1.
Yes. And V2?
x2 comma
x2
2
comma 1
comma
minus
x1
x2
minus
comma
x2.
1 minus x2.
Okay. What about V1 plus V2?
x1 plus
X1?
x
x1
plus
plus
2
x2.
plus 1 minus x1 plus
So you see
2
that you
minus
have 2
x1
minus.
plus x1 minus
2
x2.
minus x1.
Okay. So now does V1 V1 plus V2 belong to S?
No, ma'am.
No, right?
No, ma'am.
Because if this is T, then this is not 1 minus T. Right? If this is T, then this should be 1 minus T. But this is not the case. So it means that this does not belong to S. Okay. So this is again not closed under addition. Okay. Fine. What about the scalar multiplication? So let's take alpha times of x comma 1 minus x. Then what happens? Alpha x comma alpha minus alpha x. Now what can you see about alpha plus alpha minus alpha x? This should be actually equal to 1, but this is actually equal to alpha. And again, this need not be 1.
Yes.
So this
Yes.
does
One more
not
time.
belongs to.
Can you repeat one more time?
Okay. See, what we are trying to see whether the scalar multiplication is there in this set, yes or not. Here we see that if you are doing the scalar multiplication, this is the set, right? And what should be the property it should satisfy? The sum of these two entries should add up to 1. What is the sum of these two entries? The sum of these two entries alpha and which need not be 1. So this is not in the set yes for all alpha. So this is not closed under scalar multiplication. Is that fine?
Yes, ma'am.
Yeah. Okay. So I'm leaving this part as a homework because now you already have an idea of how to verify this. So this part I will leave it as a homework. Okay. So try to verify whether this set is closed under addition and scalar multiplication. Okay. Fine. Okay. Equivalently, if V1 and V2 are in S, then alpha V1 plus alpha 2 V2 is also in S. So what are we doing here? We were doing two steps. What was the first step? So the first step was we were checking whether V1 plus V2 belongs to S. And the second step, we were checking whether alpha V1 belongs to S. So if I combine these two, then I can say that, so okay, first of all, I am going to see whether alpha 1 V1 belongs to S. Okay, and alpha 2 V2 belongs to S. Then I'm going to look at whether the sum is going to be in S, which is nothing but instead of checking these properties separately, I'm simply going to consider their linear combination is in S or not. Okay, checking both this is equivalent to checking whether the linear combination is there in S or not. What is a linear combination? Do you all remember? So if you have two vectors are V1 and V2, then alpha 1 V1 plus alpha 2 V2 for some alpha 1 alpha 2 scalars is a linear combination of V1 and V2, right? So this is same as checking whether the linear combination is in the set yes or not. Okay. So in general, if you have any n vectors in S and any n scalars, then their linear combination should also be in S if these two properties are satisfied. Okay. So if S is closed under scalar addition and scalar multiplication,
Yes, ma'am.
property should be, this also should be satisfied. Okay. Fine. Now, what we have seen so far, we just understood what is mean by closure under addition and closure under scalar multiplication. Right? So whether a set is closed under addition or closed under scalar multiplication or only this much we have understood. Okay. With this understanding, we move ahead to the starting point of what are vector spaces. Okay, roughly, we can think of a vector space as a collection of objects that behave similar to the vectors in the set S. Okay, so where this set S is closed under addition and scalar multiplication. Okay, so we can perform two operations on the elements of V. What can we do? We can add the elements and we can do scalar multiplication. Okay, fine. And there are few more things apart from just closure under addition and scalar multiplication. Okay, so let's see one by one. So now let us look at this particular plane, right? You are all know this is the rectangular coordinate system. In rectangular coordinate system, what does V1, V2 and V3 represent? Can anyone tell? What is V1?
Points.
Yeah, what is that
Co-
point V?
Coordinates.
1, 2.
Coordinates.
Coordinates. Yeah.
1,
And
comma
V2 is
2,
2, 1.
2
Comma
comma
1,
2 comma 1,
1,
2 comma 1,
minus
Minus
1,
1 and 1.
minus
Minus
1,
1.
2 comma 1.
okay, fine. So V1 is we have 1 comma 2, 2 comma 1 and minus 1 comma 1. Okay, what is V1 plus V2?
3, 3.
3, 3.
3 comma
3,
3,
3.
3 comma
or
3,
3,
3.
What is V2 plus V1?
3,
3
No,
comma
my,
3, again
3.
Okay, so the first thing is that addition is commutative. Okay, so the same thing you can check with V3 also. V2 plus V3 should be same as V3 plus V2. In general, you take any two vectors. Okay, in general, you take any two vectors. U plus V should be same as V plus U. Okay, so this is the
yes, ma'am. Yes.
property that addition is commutative. What is the next property? Addition is associative. What is meant by associative? When you move the brackets, then still the value should be the same. Now we already know what is V1 plus V2, which is 3 comma 3. Now what is 3 comma 3 plus minus 1 comma 1?
2, 4.
2 comma 4. What is V2 plus V3?
1, 2.
1, 2.
Okay. Now what is the sum of these two vectors?
3,
2,
4. 2, 4,
2,
sorry.
So what is that you see? V1 plus V2 first and then adding V3 is same as V1 plus V2 plus V3. So addition is associative if these values are same. Okay. And then there exists an additive identity. What does it
Yes,
mean
ma'am.
by additive identity? Let V be any vector in R2. Find a vector such that when it is added to V, the sum is still V. What is the such a vector?
0 vector.
0.
0 vector.
Yeah. Right? So for any x comma y, if you add the 0 vector, then you will again get x comma y. This 0 vector is called the additive identity. Okay, this is the additive identity. Okay, fine. Next, what is additive inverse? Find a vector such that when it is added to V, the sum is the 0 vector.
Minus B.
Negative of vector.
Negative of factor.
Okay, so if you have V is equal to x comma y, then minus V means minus x comma minus y. So this is the additive inverse of V. Okay, and what is 0 here? 0 means it's 0 comma 0, right? The vector. Okay, fine. Now we are looking at identity of scalar multiplication. Find a scalar such that when it is multiplied to V, the new vector is still V.
1.
1.
1.
And what is called the identity of scalar multiplication. Okay, fine. Similarly, associativity for scalar multiplication, you can move the brackets. So what is V1 is 1 comma 2, right?
6v1. 6v1.
Yeah. So in both the cases, it is the same. So you see that here it is 6 comma 12 and here 6 times of 1 comma 2 is again 6 comma 12. Both are same. Okay. So this is associativity for scalar multiplication. Now, what is distributivity of scalar multiplication with respect to vector addition? So now, what is 2 times
Excuse
of?
me, ma'am. Sorry to interrupt. Can you
Yes.
scroll down? Fifth point.
Yes.
I'm just noting it down.
Okay, okay. This PDF will be shared after the session. You don't have to write everything unless there is something which I am not writing here.
Okay, okay, ma'am.
All right. So here you see that this is 2 times of these two vectors, sum of these two vectors. What is the sum of these two vectors?
2 comma
3 comma 3, right? So this is 6 comma 6. Now what is 2 times of 1 comma 2 plus 2 times of 2 comma 1? 2 comma 4 plus 4 comma 2, which is 6 comma 6. So you
Ma'am,
see
here
both
ma'am
are.
V1 and V2 are from the previous
So this example, just some specific example I have taken. This is actually applicable for any V1 and V2. Just as an example, I have taken these vectors. You can try with any vector actually.
okay ma'am,
Okay.
thank you.
Fine. So here 2 plus 3 times of V1, which is 5 times of V1 is 5 comma 10. Okay. And here 2 times of 1 comma 2 plus 3 times of 1 comma 2
2
is
comma
2
4
comma 4 plus
3 comma
3
6
comma 6, which is again 5 comma 10.
5 comma.
Yes. Yes. Aisha, please ask your question.
Ma'am, in fifth point, what is 1? Is it just a real number or is it a
Yeah.
vector?
1 is a scalar.
Scalar, okay.
Scalar. Okay. So you see that these are some properties which we can see in the plane, right? So now we will formally define what are vector spaces. Okay. So now a vector space V over R is a set along with two functions. What are the two functions? First one is the addition property. So you take the function from V cross V to V defined by, you take the pair V1 comma V2, then it should map to V1 plus V2. And scalar multiplication, you take an alpha, you take a vector V, it should map to alpha times of V. Okay. So it means what? This says basically that V is closed under addition and scalar multiplication.
Ma'am, can you repeat this definition of vector spaces?
No, I have not yet completed it. I'm
I
just
have
starting.
understood actually what you.
No. See, we are just starting. We have not yet completed the definition. First of all, we are considering, okay, a set V. Okay, a set V. So whenever we are defining vector spaces, we always consider real numbers here, because for scalar multiplication, for this operation, we need real numbers. So we are considering for any set together with a scalar set, we will always define vector spaces. For defining vector spaces, we always need a scalar field. Okay. See, this is kind of indirectly saying V is closed under addition and scalar multiplication. This is the first condition we are taking to define what are vector spaces. The first condition is that the set should be closed under addition and scalar multiplication. Okay. And the set is sometimes denoted in this way. Okay. Representing the set. This is the set. This is the addition. Because addition, later on you will see in examples, can be defined in several different ways. This is the scalar multiplication. This is the scalar field. These are the parts of a vector space. Okay. And now you see one by one the properties which we have seen earlier. This is the commutativity of addition, right? Commutativity of addition which we have noted down
R
here.
is what R क्या था?
R is the set of all real numbers.
The range of the number, right?
Real numbers, not range. They are real numbers.
What is field?
Okay, let's forget about this term. They are just real numbers. Okay.
Okay.
What is a field is something, a big topic to discuss. Let's just say that this is a real numbers. Okay, fine. So what are the properties it should satisfy? All the properties which we saw, which we observed for the vectors in R2, all those should be satisfied for the set V. Okay, first is commutativity for addition, associativity, and then existence of additive inverse, additive identity, existence of additive inverse, and then existence of identity for scalar multiplication, associativity, and distributivity over scalar multiplication. So all these properties, so totally if you say we can count like 10 properties if we include these two. So the first is like closed under addition is number 1, closed under scalar multiplication is number 2, plus these 8 properties. Okay, so 1, 2, and then plus 8. So totally 10 conditions for a vector space.
Okay.
All these 10 conditions, if it is satisfied by a set V, then such a set V is called a vector space. Okay, so
Why do you call it vector space? Why not a vector set?
yes, it's a good thing. It's not a set, it is a space, because see, a set means it does not have this property. Okay, so maybe here we are looking at a plane. What about the 3D structure? Do you call it a set or a space?
Space.
Space.
See, there is much more difference between a set and a space. Why is that so? Because in a set, you don't have this closure property. It is a space. So it's kind of infinite. Okay. So space means you can always imagine that it is kind of an infinite structure, right? But set is usually not infinite. But you can see that vector spaces are kind of always going. You cannot completely draw an entire vector space in any kind of paper pen. That is not possible. So that's why the term space. You get the idea? Yeah.
Okay, yeah, but we define it as a set that follows some certain properties, right?
Yes, it is a set which follows certain properties, and if the set with additional properties becomes a space. Okay.
Okay.
To prove
Is
vector
it like
spaces,
a
so the conditions are important to prove yet pehle.
Yes, these conditions are very much important for a vector space. All these conditions.
so is Euclidean space a vector space?
Yes, R2 is a vector space. Yes. R3 is also a vector space. Okay.
And R?
Fine. R is also a vector space. Yes.
Okay.
Okay. Note that to prove a set is a vector space, we need to verify additive and multiplicative closure and all the other axioms given above. So all the 10 conditions we need to verify. Okay. If just one of the vector space axiom fails to hold, then V is not a vector space. It means what? If you are able to disprove at least one of these 10, then you can say it is not a vector space. To disprove that a given set is not a vector space, you don't have to disprove every single point. You just disprove one particular point. That is sufficient to say that it is not a vector space. But to prove something is a vector space, you need to verify all the 10 conditions. Okay, fine. So we will see some examples there. You can understand this better. Just wait for a few more minutes. Let me complete this point, and then we will see some examples for this. Okay. The zero element 0 belongs to V of a vector space is always unique. There cannot be more than one. So this 0 element, in the sense that we are talking about the additive identity. We are talking about the additive identity. Why I am specifying it as additive identity, you will know later. Okay. 0 in R and the vector 0 in V of a vector space are commonly denoted with the same symbol. Okay. Here this is a number, but this is a vector. Okay. Suppose if your V is R2, then this 0 is actually 0, 0. Okay. So from the context, you should be able to tell whether it is a scalar or a vector. Okay. So scalar multiplication, always we don't put the dot, we simply write it like this. Okay. A vector is an element in a vector of a vector space. For us, what is a vector? A vector is just an element of a vector space. Okay, fine. So the very common examples are Rn. What is Rn? Rn is nothing but set of all x1, x2, xn such that each xi is in R. Right? So n is any
X.
non-negative or not just non-negative or natural number. N is a natural number. Okay, so it can be just when n is equal to 1, it is just R. When n equal to 2, it is R2, the plane. So it is the set of all real numbers. When n equal to 2, it is the plane, R2 plane. And n equal to 3, it is the 3D space. Okay. So only up to this we can visualize. After 3D, we cannot visualize. We can only write in set. Yes.
N can be anything from 1 to infinity, right? But
Yes.
not 0.
Yes.
Okay.
Okay. The other example here is the set of all m by n matrices with real entries. This is what we started actually here. We did not start with exactly this, but some subset of that. We started with this set, yes, if you remember. It is kind of a subset of the set of all m by n matrices, right? Oh, okay. This is not matrices. No. This is a subset of Rn we started with. Here it is a subset set of all m by n matrices. For example, m2 cross 2 if I am taking. So here we are talking about set of all A, B, C, D such that your A, B, C, D are real numbers. Okay. How do you add two matrices? How do you do scalar multiplication for a matrix? You know, right? So what is the identity element for this case? What is the additive identity? Can anyone tell?
L equal to
0, 0, 0, 0. 4 times 0.
All 0, 0, 0. Right? And what is the additive inverse?
1 0
Minus A, minus B,
minus
minus C, minus D.
Yes. Okay. Fine. Okay. Then this is the set we started with. Solutions of a homogeneous system Ax is equal to 0. The first set which we started in today's session. Okay. So this is also a vector space. Okay. Fine. So these are some familiar examples of a vector space. Here we will do some more complicated set. Okay, we will try to solve them. For these sets, the properties are very straightforward. You can directly verify them. I will do something which is a little complicated. Okay, so here you see that the addition can be defined in several different ways. Okay, the addition and scalar multiplication need not be the usual addition and scalar multiplication. It can be defined in several different ways. So for example, here you see that the addition, usual addition, you know that it is x1 plus y1 and x2 plus y2. But now I am particularly defining the addition in this way. This is not the usual addition. Okay, so you see that it is x2 minus y2. Okay, if I'm defining like this, then will the set R2 be a vector space or not? So for that, here the question is, show that addition is not commutative for this set. What does mean by commutativity of addition? If you take two vectors from the set, then v1 plus v2 should be equal to, can you complete? What is
V2
additive?
plus V1.
V2 and V1.
Yes.
V2 plus V1.
V2 plus V1.
So it is v2 plus v1. Okay, let us see whether this property is satisfied or not. So v1 is x1 comma x2, v2 is y1 comma y2, let us say. Okay, now what is v1 plus v2 according to the definition? x1
x1 plus y1 comma x2 minus
Comma
y2
x2 plus y2.
minus y2.
Look at the definition. Okay, now what will be v2 plus v1?
Y1 plus
X-
Y. X1
y1 plus
Y2 minus X2.
y2 minus
So these two terms are equal. What about these two terms? Are they equal?
No, ma'am.
They are not
No,
equal.
ma'am.
Okay, these two terms are not equal. So this means V1 plus V2 is not equal to V2 plus V1. So you can see that the addition is not commutative for B. Clear? Yeah. So if
Yes,
addition is
ma'am.
not commutative, is V a vector space? Can V be a vector space?
No.
No.
No. No.
So this is not a vector space. Okay, fine.
Ma'am, why the x2 minus y2?
That's what I'm saying. You can define in whatever way you want. Okay, several different ways. See, these are functions. That's why in the beginning, instead of where is the definition of vector space? Instead of just saying that the set should be closed under addition and scalar multiplication, they are defining the addition and scalar multiplication as functions. Okay, there can, so you know that a function between two sets can be defined in so many different ways. That's why in the beginning of the definition of vector space, these are introduced as functions instead of just additive closure and scalar multiplicative closure. Okay, so these can be defined in various ways. Okay, fine.
Yes, ma'am, it is fine.
Okay, all right. So why this kind of a way? I don't know exactly how to tell. Maybe, for example, let us say that when you are going to, let us say you have quiz 1, quiz 2, and end term marks. Okay, and when you are going to write the total score, what should be usually done? Just add quiz 1 plus quiz 2 and then end term. Right, this is what is usually done. Let us say this is the usual addition, right? The total means what? Just adding everything. But you can change the way you want to write the total score, right? Maybe you can say that let's give some bonus marks, 2 marks to everyone, and then you put +2. Or let us say that some many students copied in some exam, so you put -2. Something like that you can do. Yes or no? So the total you can define in the way you want, right? Yes or no? Yeah. So
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
similarly, that's why here this addition is defined as a function. You can define in the way you want. Okay, fine. All right. So consider.
Scalar multiplication in left, ma'am. Our question.
Oh, see, only the point here is about the additive. We have to show whether addition is commutative. So there is nothing about scalar multiplication. But here you see that the scalar multiplication is the usual one. So this is not very interesting. But the question we have answered here. We have completed the
Okay.
question here. All right. Consider the set V, which is set of all x comma 1, where x is in R. Okay. Now we are defining addition and scalar multiplication as follows. Now we want to check whether V is a vector space or not. Okay. How is addition and scalar multiplication defined? See it carefully. Addition is done only for the first part, and scalar multiplication is also done for only the first component. And the second component remains the same. There is no change in the second component. Okay. This is how we are defining addition and scalar multiplication. Okay, what is the first thing we should verify for verifying whether this? What is the first condition?
Addition.
Addition commutative.
Closure under addition. First of all, is it closed under addition? What do you see? Is it closed under addition? So this is how two entries are added. Like, so let us say this is V1, this is V2, right? This is V1 plus V2. Whether V1 plus V2 is there in V?
Yes.
Yes.
Yes. So this is closed under addition. What about closure under scalar multiplication?
Yes.
So
Also
this is
yes.
of V1, which is, you see that this is C,
Yes, ma'am.
V1, maybe you
Yes,
see
ma'am.
that this belongs to V, right side belongs to V. So this is also satisfied. What is the next thing? Commutativity. What do you think about the commutativity? V1 plus V2, we already know. It is x plus y comma 1. What is V2 plus V1?
XY,
Y plus
2.
x1.
Y plus x comma 1. So you see that V1 plus V2 is same as
Correct.
2 plus V1. So this condition is also satisfied. What about the fourth one? What is the fourth one? Can anyone
Is that
remember?
associative? But is it associative?
Yes, let's check that. So let's first look at what is v1 plus v2, and then we add the third entry. Let's say that the third entry is some z comma 1. Okay, so let's add z comma 1. So you will see that now how is the addition defined. So we should add only the first component,
X
and the
plus
last,
Y plus Z.
yeah, the last component should remain 1. Okay, now what about v1 plus v2 plus v3? It is x comma 1
X,
plus
Y,
y comma 1 plus z comma 1.
Z, 1.
So what is the sum of these two entries?
Y plus Z comma
Y
1.
plus Z.
X,
Comma 1. Now again when you add, you are getting,
Y plus Z plus X comma 1.
okay. So again you see that LHS is equal to RHS. Okay. What about the next one? What is the next property?
Distributive.
No.
Additive identity.
Yes,
Additive
existence of
identity.
additive identity. Now remember that the additive identity should be an element of V. That you should remember. Okay. So let us say you are taking an element V in V. So V is some x comma 1. Okay. I want to choose, okay, some vector here. Okay, here maybe let's call it alpha comma 1 because this should also be in V. Okay, such that this is again V. What is my alpha comma? What is my alpha basically? You understand the question here? What is the additive identity? Does it exist or not? We are checking. And remember, the additive identity should be an element of V. Yeah. So what should be the alpha? So here V is x comma 1 and this is alpha comma 1. This should be equal to x comma 1. Do we have a solution? So x plus alpha comma 1. Yes, exactly. So here the additive identity is 0 comma 1. Okay, that's why here when I was telling somewhere 0 element was given. Yeah. So 0 element, you should not think that 0 element means it is all the 0, 0, 0. No. Additive identity can vary depending on how the addition and scalar multiplication are defined. So for example, here you see that this is the additive identity and 0 comma 0 is not the additive identity. Okay. In fact, 0 comma 0 does not even belong to this set. Okay. Fine. And what will be the additive inverse? What is the additive inverse? So if you have x comma 1, what is the vector you can add so that you will get the additive identity which is 0 comma 1?
Minus X comma 1.
That's all. Okay. So this is the additive inverse. Okay. So I guess now you have an idea how to check the properties. So you have remaining 7, 8, 9, 10 to complete. So please verify this yourself. Okay. Yeah. What's your doubt, Aisha?
So, ma'am, 0, comma 0 is not in this vector space, right?
Yes.
So that will that still make this a vector space valid? Then-
Yes. See, always 0 comma 0 need not, see, we always need an additive identity for a vector space. That need not be 0 comma 0.
Okay.
Okay. Remember that. Okay. So you can verify the remaining properties. You can see that these properties can also be easily verified. So this is actually a vector space. Okay. You can verify that this is actually a vector space.
Can you give me an example of a set that is closed under addition and multiplication but doesn't hold other conditions?
Yeah. For example, maybe if you take maybe let's consider the set V is, or S, let's take S is equal to set of all X comma Y, where your X comma Y both are positive. Okay. So is it closed under addition?
Yes.
Yeah.
What closed-ended scalar multiplication?
Yes.
Yes.
Yes. How can you say S for closed-ended scalar multiplication?
No.
So let's take alpha is equal to -1 because alpha is R. Take alpha equal to -1. What about alpha times of x comma y? Does it belong to S?
No.
No, right? So this is not closed under scalar multiplication. Got it?
Yeah, but I was saying that is there any set that is closed under addition and also closed under multiplication, but not that doesn't hold other condition?
Okay, so the other condition not satisfied. So this itself is an example. So this is closed under addition, closed under scalar multiplication, but it is not a vector space.
Okay, so we need to verify all 10 to
Exactly.
make sure it is vector space.
Yes.
Yeah, it's gonna be lengthy.
Okay, good. Okay, so everyone take your paper and pen. Time for you to figure out whether you are able to understand the concepts we have seen so far. Try it out yourself. I'm going to give you 5 minutes. Let's say 1 minute for each part. And after 5 minutes, we will discuss the answer. Till that, please don't put the answer in the chat or anything. Let's give time for everyone to think and work out. Okay, I will discuss the answer after 5 minutes. Start.
भाई हो गया सबका.
Yes, we'll just verify the answer after a minute. Okay. Have you all completed? How many of you need more time to complete this? Okay, how many of you have completed? Can you raise your hands? Let me see. Good. Few. But very less number out of 46. Okay, so let's discuss the solution here. Yes. Good. Okay, fine. So first condition is checking whether V is closed under addition or not. So if V is closed under addition or not, how can we check that? So here, first of all, this is the set, right? The addition is the usual addition. So the addition is not going to take any difference. So what do you think is the first condition, true or not?
True.
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 Okay. What about the second condition?
It's also true.
That's
True,
true.
ma'am.
And what is the zero element?
0,0. 0,0.
So this is also true, right? These two are true. What about the next one? R
It is also correct.
False.
No,
1 dot V equal to V. So here scalar multiplication is defined in this way. If your scalar is not equal to 0, then it is defined in this way. So 1 dot, let's say V is x comma y, then 1 dot V should be 1 times of x by 2 comma y by 1. So it should be x by 2 comma y. Is it same as V?
No.
no. No.
No.
Is it same as V?
No, ma'am.
So this is not correct. Okay. What about this one?
It's correct.
No.
Okay. So let's check whether S is true or not. So for S, you see that A times of V1 plus V2. So A, let's say that V is X1, Y1, V1 is X1, Y1, and V2 is X2, Y2. Okay. So A times of V1 plus V2 is, what is V1 plus V2? X1 plus X2, comma,
Y1 plus
Y1 plus. Okay. So now what is this?
Yes, it's true.
According to definition,
A by 2 into x1 plus x2.
A times of X1 plus X2 by 2, comma, Y1 plus
Y plus
Y2.
Y1 plus Y2 by 2. C.
Right?
Yeah, sorry. A.
So now you see that
But,
this A.
but that we can't say whether that A is equal to 0 or not equal
So
to
if it
0.
is 0, if A is 0, then in that case it is 0, 0. Let's consider the case A not equal to 0. A equal to 0 is trivial case. So I'm taking the non-trivial case. Okay, so I'm going to just rewrite them. So this is Y1 by A plus Y2 by A. Okay, now again we can split it further in this way. Ax1 by 2 plus Y1 by A, comma, Ax2 by 2 plus Y2 by A. Okay, now what is this? Again, I'm going to rewrite this. So this I can rewrite as Ax1 by 2. Did I rewrite it correctly? No, no, no. I made some mistake. I wanted to rewrite in a different way, but I wrote it wrongly. Sorry. So this is Ax1, comma, Y1 by A plus Ax2 by 2, comma, Y2 by A. And what is the first one? First one is nothing but A times of X1, Y1. And this is A times of X2, Y2. Right? So we have seen that AV1 plus V2 is same as AV1 plus AV2. Yeah. So now can we say that S is true?
Yes.
Yeah.
Yes.
Okay. What about the next option T?
Ma'am, what about 1 by 2? Where is 1 by 2?
Okay, let us check that. So now A a plus b times of v. Okay, according to the definition, it is a plus b times of x by 2, comma y by a plus b. Right? Now, what is a times of x comma y plus b times of x comma y? It is ax by 2, comma y by a plus bx by 2, comma y by b. So when you add them up, you get a plus b times of x by 2, comma y by a plus y by b.
Y by A plus Y by B.
What about y by a plus b and y by a plus y by b? Are they same or different?
Different, ma'am.
Okay, so this means they are not equal, right? So option T is incorrect.
Ma'am, can you please explain the option, last option?
In the last option, I have computed the LHS separately and RHS separately, and I see that the second coordinate of the LHS and RHS do not match. Hence, they are not equal, and hence option T is incorrect. Fine. Okay. How many of you got all the options here? Whatever answers we have discussed, everything correctly? Raise your hands. Anyone who got good? Okay, good. Very good. Anyone else? Good. Good, good. Okay. So those who are not able to figure it out, it's fine. We are just in the beginning. So as you practice more, you will be able to do it. Okay, fine. All right, let's continue. So there are some properties of vector spaces which we can observe from the earlier properties. Okay. So the first one is the cancellation law. So usually for real numbers, you can cancel out, right? So for example, if you have x plus 2 is equal to y plus 2, then what you write? You write it is equal to x. This implies x is equal to y. You can simply cancel out, right? Cancellation law. The same is applicable for vector spaces also. So if you have like 3 elements in a vector and you have this kind of an equation, then you can apply the cancellation law. You have v1 is equal to v2. Okay, so cancellation law is applicable for vector addition. Okay, so the vector 0 described in 3 is unique. What does it mean by it is unique? The additive identity here is unique. What does it mean by unique? So there cannot be anything different from this.
Varies with different spaces.
So only this is the vector which satisfies this condition. This is the
Only one value satisfies.
yeah, only vector satisfying this equation, satisfying this condition. That is the meaning that this vector is unique. Okay, and similarly, the inverse is also unique in this sense. Vector which satisfies this condition. Okay, this is also unique. Okay, fine. Okay, so just quickly summarizing the topics we have seen so far. So we first understood what is meant by closure under addition and closure under scalar multiplication, right? And then using this understanding, we defined what are vector spaces. For vector spaces, first condition is that based on the addition and scalar multiplication defined, the set should be closed under that particular addition and that scalar multiplication. And then it should satisfy remaining 8 axioms, right? And to verify a given set is a vector space, you need to verify all the axioms. But if you are going to disprove that it is not a vector space, it is enough if you say that even one of the property fails, then it cannot be a vector space. All right. And then you see that cancellation law is applicable, and then the zero vector is unique and the additive inverse is unique. Okay. These are some things we have seen so far. Moving to the next important topic, which is subspaces. Okay. Subspaces are comparatively easier to verify. So because here for subspaces, basically only one condition, or maybe we can split it as 2 conditions instead of so many conditions. Only this much is sufficient for a subspace. What is first of all a subspace? A subspace is a non-empty subset of a vector space. Okay, it is a non-empty subspace of a subset of a vector space, and it satisfies these two conditions. It is closed under addition and scalar multiplication. Only these two, if it satisfies, then we call it a subspace. Okay, so we don't need all the vector space axioms for a subspace. Just the closure under addition and scalar multiplication is enough. Okay, so a subspace, we say it is proper if it is a proper subset of V. Okay, so let's see some examples here. So for any vector space V itself is a subspace of V, because we can say V is always a subset of V, and we already know that V is closed under addition and scalar multiplication. So this is a subspace. Okay, and also the same zero vector, right? Zero vector in the sense the additive identity, only this singleton set is also a subspace. Why? When you add 0 plus 0, it is again going to be 0. So all the operation, and also alpha times of 0 is again 0. So obviously this is closed under addition and scalar multiplication, right? So these are called the trivial subspaces. Okay. Now let us see some non-trivial cases. Consider this. Okay. In R2, what does this represent? This is the set of all x comma y such that x plus y is equal to 0. In R2, what does this represent? Can anyone say? If you plot all these points, what will you get?
A straight line is
It's
to
a
the
2D.
origin.
Yes. So it is a straight line passing through the origin. Now the question is this a subspace or not? Okay, so we have to look for two conditions. The first one is closure under addition, right? So again, for this, we can rewrite for simplicity. So you can rewrite it as x comma minus x, x in R. Okay, so because here y is equal to minus x. So I'm replacing y with minus x. Okay, so let me take two vectors. Let's say w1 comma w2 in w. So w1 is, let's say, x1 comma minus x1. w2 is x2 comma minus x2. Now what is w1 plus w2? It is x1 plus x2 comma minus x1 minus x2, which is x1 plus x2 comma minus of x1 plus x2. So this obviously belongs to the set W. So this is closed under addition. Right? Now what about the next property, scalar multiplication? Alpha times of W1 is alpha x1 comma minus alpha x1. Obviously this also belongs to W. So this is closed under scalar multiplication. Right? So W is a subspace of R2. Okay, is this fine? How W is a subspace, this verification process you all understood, right? Okay.
Yes, ma'am.
Okay, so this is the geometrical representation of the above set. Why this geometrical representation is given here? Because there is something important we need to observe. From the above graph, it is clear that the line L passes through the origin. In general, a line in R2 is a subspace of R2 if and only if it passes through the origin. Right? Can we just go back and check this? So earlier we saw this set. Yeah. So is this a line passing through origin?
No.
No. So we see that this is not a line passing through origin, and hence it is not closed under addition and scalar multiplication. Similarly, look at this set. Yeah, this one. Is this passing through origin? Again, no. Right? This does not pass through the origin, and hence this is also not a subspace. Under the usual addition and scalar multiplication. This is under the usual addition and scalar multiplication. They are not subspaces of R2. Okay, fine. So for under usual addition and scalar multiplication, so remember, so it's a subspace of R2. Remember, this is under usual addition, unless the operations are mentioned, you always consider the usual addition and scalar multiplication. Okay, if no operation is defined for addition and scalar multiplication, we assume the usual one. Okay, fine. Now look at this parabola. We want to check whether W is a vector space of V or not. Okay, what is the first step? What is the first step?
Vector addition.
Yeah. So here is one thing everyone should note. Listen carefully. To disprove a set is okay. To disprove any property, in fact, to disprove a property, we can pick specific vectors. Okay. So here you see that. So let us take these 2 points, specific points. What is this point? Can you say?
-1, 1.
-1,
Point?
1,1.
So let us call this is W1 and this is W2. What is W1 plus W2?
0, 2.
What is 0, 2? It is here. Is it there in this set? W.
No. No.
No, ma'am.
So you can see that W is not closed under addition. So can W be a subspace?
No.
No.
No, ma'am. Okay. So remember, we can pick specific vectors only when disproving. But for proving, you cannot do like picking specific vectors is not allowed for proving. For proving, you have to pick general vectors like x1, y1, x2, y2, something like that. Okay. You cannot pick specific vectors for proving. For disproving, we can pick. Okay. Fine. So here is one important note. What is that note? So maybe you can verify it later. The only non-trivial subspaces of R2 are straight lines passing through origin. Okay, what are the non-trivial subspaces of R2? Straight lines passing through origin. Okay, fine. All right. So, okay, now here is a little different example. Okay, so this is not any subset of any Euclidean spaces R2, R3 or anything. This is set of all subset of a matrix set. Okay, now we have W, which is set of all 2 by 2 matrices such that it satisfies this condition that A equal to A transpose. Okay, so it means we are considering the set of all symmetric matrices. Now, is this a subspace or not? How do you verify? What is the first step? What is the first step?
Closed.
Yeah.
Vector addition.
Two vectors from the set and check whether they are closed under addition. What is A1 plus A2 whole transpose? It is A1 transpose.
Plus A2 plus.
Okay. And what is A1 transpose? A1 and A2
A2.
is A2. So A1 plus A2 whole transpose is A1 plus A2 and hence A1 plus A2 belongs to W. So first property closure under addition is satisfied. What about the second one? Alpha times of A whole transpose is alpha times of A transpose. And what is alpha times of A transpose? A transpose is equal to A.
Alpha
Alpha
A.
A.
So you see that alpha A transpose is equal to alpha A. This is
Means
in
it belongs to the
W. So
W.
second property. So W is a subspace of which set? M2 by 2 of R. the set of all 2 by 2 matrices. Okay, so this is a subspace of the set of all 2 by 2 matrices. Is that clear?
Yes.
Yeah. Good.
Yep.
Okay. So can you try this yourself? Check whether the set of all 2 by 2 invertible matrices with real entries with usual addition and scalar multiplication is a subspace or not. Everyone try it yourself.
Not, ma'am.
So what's the answer? Is it a subspace or not?
Not, ma'am.
Okay. So how are you saying that it is not a subspace?
Close under addition, ma'am.
Yeah. So what is
Close
that
under
you
multiplication.
are using to say that it is not closed under addition? So let us take two
And
invertible
they are
matrices.
saying they are invertible, but A plus B may not be invertible. May or may not be invertible. So that's why.
Yes. Yes. So in such scenarios, you are able to guess that A plus so sum of two invertible matrices need not be invertible. In such scenarios, pick specific examples to make your statement concrete. Okay. So how can we do that? Maybe pick some simple case. So let us say your A1 is ABCD. Okay. So if I am taking A2 is equal to minus A minus B minus C minus D. Okay, if this is invertible, what is the condition for invertibility? Can anyone tell?
It cannot
Determinant,
equal zero.
determinant of A.
Not equal to 0.
So AD minus BC is non-zero, right? So determinant of A1, which is AD minus BC, is non-zero. Now, what can you say about determinant of A2? Again,
Is
say this.
also non-zero.
Not equal to
Okay, so both are A1 and A2, both are invertible matrices. Now, what is A1 plus A2? Is this invertible?
No.
No, ma'am.
Okay, so W is not a subspace. All right, clear? Okay, so let's try something from R3 now, subset of R3. Now we want to, so they are already saying that it is a subspace and we want to verify. So we have to pick two vectors from this set and we want to check whether it is a subspace. Let's say 0, y1, z1. Obviously, this is a subspace, right? Very straightforward to check. So maybe I will leave it as a homework because this is very straightforward to verify. Okay, so this is a subspace. What about this one? Is this a subspace? Okay, here something we need to observe here. This is a plane in R2, right? So note W is a plane in R2. Okay, W is a plane in R2. Okay, now if W is a plane in R2, we also note that this is passing through origin. The other thing is that it is passing through origin. Okay, now what about this W? This is also a plane. This is also a plane,
Not a
but
subspace.
not, yeah, and this is
Because
not
it's not
passing
passing
through
through the
origin.
origin. Okay.
Okay, so this is the hint we need to take, whether it is in R2, so whether the line is passing through origin or not, and if it is R3, whether the plane is passing through origin or not. So specific examples also we can take, or if we can take like two vectors W1, W2, like x1, y1, z1, and x2, y2, z2. You see that W1 plus W2 means you have x1 plus x2, y1 plus y2, z1 plus z2. Now what do we already know? X1 plus y1 plus z1 is 1. X2 plus y2 plus z2 is 1. Now what is x1 plus x2 plus y1 plus y2 plus z1 plus z2?
2.
2.
2.
So this means that this does not belong to W. So this is not a subspace. Okay, fine. All right. Okay. A subspace, this is also a subset of R3, but you see now it is defined a little differently. Take a couple of minutes and see how you can disprove that it is not a vector space. They are already saying that it is not a vector subspace. Think of some specific ways to disprove this, that it is not a subspace. How can we do this?
0, 0 doesn't lie.
0, 0.
0. Origin.
You have a equality,
Okay.
so it is there.
Okay.
Origin is there. Equality is there, right?
Okay.
Okay, so maybe I will give a hint. Try disproving scalar multiplicative property. That is easier. Try disproving using scalar multiplication property.
In that we can multiply some negative number like
Yeah. So for example,
Multiplication by a negative number changes.
yeah. So you see that this belongs to W because 2 is greater equal to 1. Now if I am multiplying with minus 1, for example, 2, 0, 1, then it is minus 2, 0, minus 1. And you see that here this minus 2 is strictly less than minus 1. So this does not belong to W. So W is not a subspace. Okay, so when you are involved, you can take a guess that you can use scalar multiplication. Okay, fine. Yes. What's your question, Kamalesh?
yes, ma'am. Actually, not related to this question, but like while solving questions based on vector space as R square or like R2, in that while multiplying the that scalar quantity, won't that become a positive number? Like we always get a positive vector or something.
Nothing like that. You just they are like multiplication of real numbers. Just like you multiply real numbers, you have to do the multiplication with each component. The sign will not change automatically unless you are defining something specifically in that way.
So we can
You,
multiply negative number in that case.
yes, that is allowed because real numbers include negative numbers, right?
Yes, ma'am. Yes.
Yeah. All right. So in general, what are all the possible subspaces of R2? So these two are the trivial cases. So these two are the trivial cases. And this is the non-trivial case. Any line through origin. Lines which are not passing through origin are not subspaces. Okay, fine. So the zero subspace, line through origin, the entire subspace R2. These are the subspaces of R2. Okay. And similarly, what are the subspaces of R3? The trivial subspaces, the zero subspace, the entire space R3. Okay. Lines through origin and planes through origin. So these are all the possible subspaces of R3. Okay. Fine. Okay. So consider this following sets V1, V2, V3, V4, V5. So these are all subsets of the 2 by 2 matrices. The first one we already know. What do we know about V1? Is it a subspace or not?
Yes, it is a subspace.
So V1 is a subspace we know. What do we know about V2? We have to check V2. So what is V2? V2 is set of all scalar matrices. What is mean by scalar matrix? Can anyone tell?
Matrix having diagonal elements.
Non-diagonal elements are 0.
0.
And all diagonal elements are same.
Okay, so these are the set of all 2 by 2 matrices. Now we want to see whether this is closed under addition and scalar multiplication. So let's take any two matrices from here. Let's say A1 comma A2 in V2. So let's say A1 is alpha 1 0 0 alpha 1. A2 is alpha 2 0 0 alpha 2. I'm not doing any calculation. Straight away, are you able to see whether this is a subspace or not? Whether it is closed and addition?
Yes, it is a subspaces.
Yes. So you see that this is a subspace. Okay. What about diagonal matrices? Again, diagonal matrices means they are all
Also same.
yeah.
Same.
So
The diagonal entries are same.
they are not same. For diagonal entries need not be same for diagonal matrices. Only for scalar matrices, the diagonal entries are same. Here it can be different. Okay. So what do you think about V3? Will it be a subspace?
Yes.
This is also a subspace you can verify.
Yes.
What about upper triangular matrices?
No, ma'am.
Why not? What is wrong with upper triangular matrices? So upper triangular matrices in the sense V4 is set of all A, B, 0, C, A, B, C in R. So take any two upper triangular matrix. Will it be again upper triangular? The sum? Yeah. What's the answer? Will V4 be a subspace or not?
Yes.
It is a subspace. You can verify. Those of you who have doubt, you can verify that it is a subspace. Similarly, the set of all lower triangular matrices. So these are upper triangular and these are lower triangular. You see, all of them are actually subspaces. Okay, so those you still have doubts, these are very simple, straightforward cases. So you can verify that all of them are subspaces. Okay, fine. So here I give you a simple homework. Try this one. Let's say you have V is equal to set of all A, B, C, D, such that A plus D is equal to 0. Is this a subspace? You have to verify. Okay. Is this a subspace? Okay. Verify this. All right. So we are moving to the next very important concept, which is linear combination. Okay. What is linear combination? You have already seen or not in week 1 and week 2. Have you seen this term earlier, linear combination?
Yes, ma'am.
Right? You already know what is linear combination, right? So if you have a set of vectors v1, v2, the linear combination v1 plus v2 plus so v1 of v1, v2, vn is summation I equal to 1 to n ai va, right? So a1 v1 plus a2 v2 plus etc. an vn, right? So this is a linear combination of v1, v2, vn, right? So here is some graphical representation of linear combination. So let's say you have two vectors x1 and x2. So what happens in a linear combination? You first do the scalar multiplication of x1, scalar multiplication of x2, add them up. So this is the linear combination. So this is the representation in R2. Okay, so this is something which you already know. Okay, fine. So now can you express any vector x comma y as a linear combination of v1 and v2? The question is, can you write x comma y as a linear combination of v1 and v2?
Yes, ma'am.
So can you find alpha 1 and alpha 2 such that this is satisfied? What are the alpha 1 and alpha 2 which satisfies this condition? Can you find it first of all? If you
Alphas
are,
are scalar values.
sorry?
Alphas are constants.
Yeah, so what are the constants? Let's say your first coordinate is x, second coordinate is y. So here you see that this is alpha 1 times of 1 comma 0 and this is alpha 2 times of 0 comma 1. So what does this say? So this is alpha 1 comma 0 comma alpha 2. So this is alpha 1 comma alpha 2. So equating the components on the LHS and RHS, you see x is equal to alpha 1 and y is equal to alpha 2. So yes, you can write x comma y as a linear combination where alpha 1 is equal to x and alpha 2 is equal to y. Okay, so the answer is yes. Okay, so for example, if I am taking minus 2 comma 3, then I can write minus 2 comma 3 as minus 2 times of v1 plus 3 times of v2. Okay, fine. Now try this one. Can you write v as a linear combination of v1 and v2? Okay, there is something important I missed to ask. Whether v1 and v2, are they linearly independent? Are they linearly independent?
Yes.
v1 and v2 are independent.
Ma'am, ma'am, can you please explain this line?
Linearly independent means for two vectors, at least you can say that neither of them is other. Okay, v1 is not equal to alpha times of v2 for any alpha. You cannot write one as a scalar multiple of the other. So this is the case for two vectors. For n vectors, the definition is different. Okay, so let's first go step by step. We start with two vectors and then we go step by step. Okay, now the question is, can you write v as a linear combination of v1 and v2? So what do you note about v1 and v2? Are they linearly independent?
Yes, ma'am.
So again, v1 and v2 are linearly independent. Okay, so now we are checking whether you can write 5 comma 6 as alpha times of 1 comma 2, or let's say alpha 1 times of 1 comma 2 and alpha 2 times of 1. Okay, so now you, to find alpha 1 alpha 2, you need to solve system of linear equation. What are those? So 5 comma 6 is equal to alpha 1 plus alpha 2 comma 2 alpha 1 plus alpha 2. This step, is it fine? I have just simplified the RHS.
Yes, ma'am.
So now equate the components on the LHS and RHS. You get a system of linear equation. System of linear equation and check whether there is a solution or not.
1,
Al-
y is 4.
alpha 1 is equal to 1 and alpha 2 is equal to 4.
Okay. Yes, first equation is satisfied. Second equation is also satisfied. Yes. So the answer for the given question is,
Is linear combination.
yes, you can write V as a linear combination of V1 and V2. Okay. So this one, I will leave it as a homework. Write V as a linear
How to
combination.
check it is independent or not?
Sorry, what?
Independent. How to check?
See, independence for two vectors, you can check in this way. Can you write one as a multiple of the others? Alpha times of 1, 0 is always of the form alpha 0. It cannot be of the form 0, 1. Similarly, alpha times of 1, 2 means the second should be always a multiple of the first. So 2 times of the first one. So you see, obviously, they are not multiples of each other. Right? So for example, if you take these two vectors, 2, comma 3 and 4, comma 6. Do you see that they are multiples of V1 and suppose this is V2? You observe that these two are multiples of each other. It means that V2 is 2 times of V1. Do you see that? In this case, we call V1 and V2 are linearly independent. Sorry, linearly dependent. Okay, they are not linearly independent because you are able to such that this is satisfied. So this part is a
Ma'am,
homework for you. Yeah.
फिर
Can you
0
show
and
the
1 है कितने what?
homework,
Sorry, what?
previous homework question?
Which question?
Previous homework that you given us.
This one?
Not this one, not this one. That previous one.
When you start before the starting of linear combination, I think so.
This one,
Yeah,
right?
yeah, this one.
You want to note it down or what are you asking?
I'm taking screenshot.
Okay, fine. All right, shall I scroll down? Anyway, these notes will be shared with you.
Yes, ma'am.
Okay, fine.
How are you going to share it, ma'am?
Okay, so I showed you a sheet which in the beginning of the session, the schedule. Do you remember that?
Yes.
So there you see that you have instructor session notes. There is a drive link. In the drive link, all the instructor session notes are available.
Thanks, ma'am.
Ma'am, can you please share this in chat section, just like you shared in our previous terms?
I have already in chat section. I never share any notes. No. Okay.
No, madam, the link of the drive, she's saying.
That I have
Yeah.
already shared. I guess I've shared already. Okay.
Ma'am, can you please again say share it? Like I can't find this.
So both the sheet link, the drive link, everything is there. See, the sheet link is the most important one. If you open the sheet, then everything is there. The YouTube playlist, instructor session notes, TA session recording, everything is there in the sheet. Okay. I have pinned the sheet link. Okay. All right. Okay. So why we are looking at the linear combination? Because we are going to see something very important here. Okay. So note that if V1, V2 are vectors such that V equal to A1, V1 plus A2, V2, then each of the vector is a linear combination of the other two vectors. Right? We can just simply do some rearrangement and we can write the other vectors also as a linear combination, assuming that A1 and A2 are non-zero. Okay, fine. Now, further 0 can be written as a linear combination of V1 and V2. How can we write? So, suppose you have this condition. How can you write 0 as a linear combination of V1 and V2? How can you write 0 as a linear combination of V1 and V2? What are the coefficients you should have? You can have.
Zero coefficients.
Yeah, 0 coefficient is obviously a one case. Yeah. What is then other case?
something after which addition it becomes zero, addition or subtraction automatically.
Yeah, so here already you have this equation. From here, how can you find the coefficients? Come on, just simple rearrangement of the equation.
Ma'am, ultimately it boils down to finding as a linear combination of V1 and V2 because V itself can be expressed.
See, this is given to you. If this is
Ma'am,
given, how can you
V
write
plus
0 as a
V1 is equal to minus V2.
Coefficient of V is -1.
yes? And this is A1, P1. That's all, right? So when you bring V to the other side, you automatically get 0, right? Okay. Okay, so here it is A2. Sorry, A2. Okay, fine. Okay, so in that case, now you see that these vectors have non-zero coefficients and the sum is 0. So what is that? Here we have, so, okay, there are so many observations I have done here. So you see V1, V2, V3. So again, you see that any x comma y comma z can be written as xv1 plus yv2 and zv3. Okay. Similarly, how can we check whether these three vectors, so this is kind of a little more involved. So this again, you need to solve system of linear equations. Can you write 372 as a linear combination of a1 v1 plus a2 v2 as a linear combination of v1 and v2? Are v1 and v2 linearly independent?
Yes, ma'am.
Yes. So v1 and v2 are linearly independent. Okay, that is there. But now we are in R3. So we have to check whether V belongs to the span of V1 and V2. So whether the term span is already introduced to you?
No.
No, man.
No.
It is simply a set of all possible linear equations. Okay. So I guess we have introduced it a little later, maybe. Maybe not in this question. In the next question, maybe we will
Can you repeat span?
okay. So span of a set of vectors V1, V2 is all possible linear combinations of V1 and V2. So it is the set of all AV1 plus A1 V1 plus A2 V2 where your A1 and A2 vary over R. Okay. So now you will be able to find A1 in A2 if your V belongs to, so is V in the span of V1 V2. So for that you need to solve system of linear equation and check whether it is there or not. Okay. So what is so the plane that contains these 2 points is given by this equation. So what are these 2 points I am telling? V1 and V2. Okay. You see that this plane is nothing but span of V1, V2. Okay. When you take the span of these two vectors, what you will get is a plane. Okay. Always when you are going to do a span of two linearly independent vectors, a plane. So just like in the previous scenario, the span of these two linearly independent gives us the entire R2 because any vector is a linear combination of V1 and V2. It means what? The entire R2 is in the span of V1, V2. You understand that? So span of what is the span of V1, V2 in this case? Entire R2.
हो गया शायद.
I think ma'am left.
Okay, all are those left.
I have a question here. कि उन्होंने जो डॉक्यूमेंट शेयर किया है दैट्स अ स्प्रेडशीट, वहीं पे बहुत सारे लिंक्स है बट वो तो मतलब खोल ही नहीं रहा है क्योंकि इट्स जस्ट फॉर द व्यू।
मैं बताता हूँ। जब तुम में ओपन करोगे तो वहाँ पे नीचे सीट वाला ऑप्शन दिख रहेगा, तो वहाँ पे क्लिक करने से हो जाएगा। जब आप मतलब मीटिंग में ज्वाइन करोगे
There was
तो
a power
वहाँ
cut
पे
from my
सीट
side.
वाला ऑप्शन रहेगा, तो उससे हो जाएगा।
Ma'am, can you repeat?
Yeah, sorry, there was a power cut. Okay, so what I was saying is that span of V1, V2 is equal to R2. Okay, so what is mean by span? All possible linear combination, right? So if I'm doing all possible linear combination, then what will I get? So any vector in R2, you see that I can write any vector x comma y I'm taking in R2. So I'm taking x comma y in R2. And I was able to write x comma y as a linear combination of alpha 1 v1 plus alpha 2 v2. It means what? X comma y belongs to span of v1 v2. So from this, can I say R2 is a subset of span of v1 v2? Yes or no?
Yes, ma'am.
So the other way around is obvious, right? Because this is obviously a subspace or a subset of R2, right? Span of v1 v2 should be a subspace, a subset of R2, so they should be equal. Okay, fine. Maybe we'll go step by step again. So where were we? We are in R3 where we are having a vector and we want to check whether this vector is a linear combination of v1 and v2. So v1 and v2, are they linearly independent? So can we write v1 as a multiple of v2? Yes or no? Can we
No.
write? No. So they are
No.
linearly independent. Okay. So what are the things we need to observe? If V is a linear combination of the vectors v1 and v2, does V lie in the plane containing v1 and v2? What is your answer? What is your guess? Suppose your V is a linear combination of the vectors. So
If
your
they are a linear combination, then it can plot into the graph
V
in a
is equal
plane.
to, see, you are having a v1 plus a2 v2. You have this. Okay. Now v1 and v2 are in some plane. Can you say that this linear combination is also in the plane? What do you know
Yes.
about a plane? What do you know about a plane? Let's say plane passing through origin. What do you know about a plane passing through origin? Is it a subspace?
Yeah.
Yes.
So
Yes.
by
Yes.
subspace,
If it is passes through the origin, that
it's
it
a
means
subspace.
yeah.
Yeah. Right. So the answer is yes, because you see that when you take a linear combination for any plane passing through origin, this should obviously be in that plane.
But it's not given that it's passing through the origin, right?
Because here why I am saying that this V does V lie in the plane containing v1 and v2. See, we are considering, maybe I should be more precise. So I should say that what is span of v1 v2?
All linear combinations.
So when I'm considering all linear combination, does it contain 0 or not?
Yes.
Yes.
Okay. So here my question is that suppose I am considering the span of v1 v2. This is the plane I am talking about. Okay. So will any linear combination be there or not? So it will obviously be there. Okay.
Yes.
So in the span of v1 v2, I have is the
Because
plane.
it's passing from zero, that's why.
Sorry, what?
Because it's passing from zero, that's why.
Yes, yes.
Ma'am, how zero is a
Okay. Some more
zero lies
observation.
on the plane because it is a plane in the space actually.
Yes. So let us say I'm not very good in drawing 3D structures, but yeah, let me try something. So let's say you have
A1 V1 plus A2 V2 will be equal to 0, right? It is possible. That's what I'm saying.
see.
I guess.
Suppose you are having some 3D structure like this. Okay, let me say that this is your x, y, and this is your z axis. Okay, suppose as a very simple scenario I am taking, I am going to take the xy plane itself. Okay, so this is the xy plane. Now, does it contain the origin or not?
Yes.
Okay, so yeah, so there can be, suppose I'm going to take some other plane, for example, some plane which is here maybe. Okay, which is not passing through origin, that is also possible. So something where plane which is parallel to the xy plane but lying above the plane, so it is not passing through origin. So you can have both planes passing through origin and not passing through origin. Both are possible. Okay. Okay. Now let W be 1, 2, 0. Is this vector lying in the plane or not? How do you verify whether this vector lying in the plane or not?
If it satisfies the equation.
Yes. So now let's try 2 times of 1 minus 2 times of 2 plus 4 times of 0. What's the answer? 2 minus 4 plus 0 is minus 2 and not equal to 0. So W does not lie on the plane W. Correct? So lie on the plane, maybe I'll write lie on the plane. Now the question is, can we write W as a linear combination of V1 and V2? Remember, V1 and V2 are lying on this plane 2x minus 2y plus 4z. Remember, 0 to 1 and 2 to 0. 0 to 1 and 2 to 0. They are lying on this plane. Do you see that? So 2 times of 0 minus 2 times of 2 plus 4 times of 1 is 0. Similarly, 2 times of 2 minus 2 times of 2 plus 4 times of 0 is 0. So these two, V1 and V2, belong to the plane, lie on the plane. Okay. Now you have another point which does not lie on the plane. Now the question is, can I write W as a linear combination of V1, V2? Shall we quickly check this? Alpha 1 V1 plus alpha 2 V2. Everyone take your paper and pen and let's solve the system of linear equation which you get from here and see whether this system has a solution or not. So you have 2 alpha 2 is equal to 1. 2 alpha 1 plus 2 alpha 2 equal to 2.
Alpha 1 equal to 0.
And alpha 2 equal to 1 by 2. Now let's substitute it here. 2 times of 0 plus 2 times of 1 by 2 is 0 plus 1. It is not equal to 2. So, no solution. What does this mean? You cannot write 1, 2, 0 as a linear combination of V1 and V2. So, the answer is no. So, what have we done here? We have taken one point which is not in the plane and 2 points which are lying on the plane. So, the point which is not on the plane cannot be expressed as a linear combination of these two vectors which are on the plane. This is an important observation. How did we get this observation? Is this part clear for everyone?
Yes, ma'am. Now can we say directly also, if this is not in plane, then also it's not a linear possible?
Sorry, what?
Now can we say directly also, if this point is on the plane, so linear thinking is not possible of these points?
Yes, but what is the background? What is the exact explanation behind? I have just explained it here. Okay,
Okay.
fine. Now, can we write 0 as a linear combination of the vectors v1, v2, and w? v1, v2, and w can be write as a linear combination of 0. So, v1, so alpha 1 v1 plus alpha 2 v2 plus alpha 3 w equal to 0. Is this possible?
No, no.
Why it is not possible?
Because V1 and V2 lie in a plane and W lie in another plane. So
Yeah, so we do not have something like this. W is not equal to alpha 1 v1 plus alpha 2 v2 for any alpha 1 v1, alpha 1 alpha 2. So this is also not possible. So the only possible solution is alpha 1 alpha 2 alpha 3 are 0. Okay, what is the only possible solution?
All
Alpha
the
1
coefficients
alpha 2.
zero.
all are 0.
Yeah. So here earlier we had a scenario that here we are able to write all these three vectors like with non-zero coefficients. So here v1, v2, we were able to write 0 as a linear combination with non-zero coefficients. But here we have again three vectors, but we don't have any non-zero coefficients. There is a big difference. Now we will introduce the definition. Here is another example. Maybe we'll come back to this again. A set of vectors v1, v2, vn from a vector space V is said to be linearly dependent if there exist scalars a1, a2, an, not all zero, such that a1, v1 plus a2, v2 plus etc. an, vn equal to 0. What does this mean? So let us say you are in R2. Okay. In R2, I'm having some vector, let us say 1, comma 1. Okay, and I'm having some other vector, maybe let us say 1, comma 2. Okay, I'm having two vectors. Now these two vectors, are they lying on the same line or are they lying on different lines?
Different line.
Yes. Okay, first observation, v1 and v2 do not lie on the same line through origin. Right? Okay. What is the next observation? V1 is not equal to alpha V2 for any alpha. Yes or no?
Yes, ma'am.
So this means what?
Yes,
This
ma'am.
means what? V1
They are
minus
independent.
the plus or minus whatever. So suppose you have a equation like this: alpha 1 V1 plus alpha 2 V2 equal to 0. What are the possible values for alpha 1 and alpha 2? What are the possible values
Alpha
for
one,
alpha?
Alpha 1 is equal
1,
to 0, alpha
2
2 is
and
equal to 0.
alpha 2 1, 1.
This is the only possible solution because V1 is not equal to alpha V2 for any alpha. So the only possible solution is alpha 1 and alpha 2. So now in this scenario, we are calling V1 and V2 are linearly independent. Okay. So we started with two vectors not being scalar multiples of each other. They are lying on different lines. Then you see that alpha 1 v1 plus alpha 2 v2 implies both the coefficients are 0. So this is the definition of linear independence. I guess I have kept the definition for the next session. So now let us take another vector which is on the same line as that of 1, comma 1. Maybe I will take minus 1, comma 1. Minus 1, comma minus 1. Now I'm having, let's call this maybe V3. Now what can we say about V1 and V3? So for V1 and V3, can I find alpha 1 and alpha 2 such that this is equal to 0? V3. Can I find alpha 1, alpha 2 such that the linear combination is 0?
Yes, ma'am.
Yes, ma'am.
What are the coefficients? Alpha 1 equal to
1 and
1,
1.
alpha 2 is equal to 1. So you have non-zero coefficients, just like you have in the following definition. If you have non-zero coefficients, then you say these vectors as linearly dependent. You call them linearly dependent.
Depend.
So you see that we are linearly dependent. Do you visually understand, like from the graphical point and also from the definition, In both ways, are you able to understand linear dependence and independence for at least R2 till now?
Yes,
Yes?
ma'am.
Yes, ma'am.
Okay.
Yes,
Now,
ma'am.
sorry, what? Okay. So there is something more now we can see from the definition. So in the definition, it says that if you are able to write any set of vectors as a linear combination of non-zero coefficients and it is equal to 0, then what did we see here in this scenario? V1 and V2, they are linearly dependent or independent? Linearly
Dependent.
dependent, because you have
Dependent.
non-zero coefficients, so they are linearly dependent.
Yes,
Okay.
yes, yes.
Yeah, in general, you can figure out that any three vectors two are always linearly dependent. Okay, any three vectors in R2 are always linearly dependent. This you can check because just two vectors are sufficient to just span the entire plane. If you are going to take three vectors, then obviously you are going to be able to express one of the vectors as a linear combination of the other two. So any three vectors, you will always see that they are linearly dependent. They can never be linearly independent. Okay, if you are having three linearly independent vectors, then those vectors cannot be from R2. Okay, then you will have to move to the three-dimensional space. Okay, so the number of linearly independent vectors in R2 is maximum 2. Okay, now let's look at this question. So this is something based on just the property of linear combination V1, V2, V3. So V1 is this, V2 is this, and V3 is this. Now the question is find out the correct option. 2 comma 3 is equal to what? 2V1 plus 0V2 plus V3. Is this correct or not?
Yes,
Correct,
ma'am.
ma'am.
Correct. What about the second one?
Yes, ma'am. It is also correct.
Okay. What about the third one?
No.
So you have 2 comma 2,
No.
1 comma 0 plus 0. So it is actually 3 comma 2.
3 comma 2.
And this one?
It is also 3 comma 2.
Not correct.
So this is also 3 comma 2. Not correct. So you see that the same vector we are able to express as different linear combinations of V1, V2, V3. This is another observation. Okay, so let me quickly summarize and we will wind up the session. What are the things we have seen? After introducing vector spaces, what are linear combinations, right? What is mean by linear independence and what is linear dependence? At least in R2, you should have a very clear understanding about what is mean by linear independence and dependence. Okay, both geometrically as well as based on definition, you should have a very clear understanding. Okay, up to this, is it fine?
Geometrically, how linear independence we can verify?
That's what I'm saying. If they are in different directions and not lying on the same line, or see, two ways you can say. So one thing is that V1, V2 in R2, if V1, V2, they are on same line through origin, then
So if
they are
alphas are 0, we can say independent. No?
scalar multiples of each other. So in this case, we say that they are linearly dependent.
Independent.
Dependent.
Yes, ma'am. Dependent.
Okay, if they are on the same line through origin or they are scalar multiples of each other, they are linearly dependent. Okay, is it fine up to this?
And if alphas are 0, we can say that it is independent.
Yes,
No?
ma'am.
Sorry, what?
And if alphas are 0, we can say it is independent.
Yeah, so suppose this equation, the only solution is all of them are 0, then in that case we can say that they are linearly independent. Yes. Okay. Fine. So we will continue with the linear independence definition and the further topics in the next session. So in today's session, we have covered this, and also started this. Maybe we will see more on this in the next session. Okay, fine.
Ma'am, next session you will take, no?
Next session will most probably not by me. Okay. All right.
Thank
Anyway,
you, ma'am.
yeah. Thank you all. See you again in some
Ma'am,
other session. Yeah.
Thank you.
are those the only topics in week 3?
Sorry. In week 3, what?
Are those whatever